I wanted to show you guys our Wimshurst machine. This was originally invented to continuously separate charges so that you could have a constant flow of charges, what's called an electric current, for using in different electrical experiments. Nowadays we mostly just use it to generate big sparks. The most important part of a Wimshurst machine are these discs, which are made out of some insulating material. And on it there's all these conductors that electrons are free to move within, but they can't move across the discs and they can't move between the different plates. It's actually not just one disc, it's two discs. And they're hooked up to a crank, and the pulleys are set up differently. This one is straight, this one is crossed, so that when I turn the crank, they move in opposite directions. Well, what does that accomplish? The job of a Wimshurst machine is to separate charges, and it does this through a process called induction. Here's how it works. Notice that this segment here is hooked up through the brushes to the opposite segment. And imagine that the segment on the other side, on the other wheel, across from this, just happens to have a positive charge. Well, what's going to happen? Electrons in this segment will want to get as close to it as they can, but they can't go through the insulator, so they'll just kind of line up on the inside of this foil. In addition, since there's a connection to this guy, electrons are actually going to leave this and they're going to go up, and they're going to go through this brush and they're going to pile on this. So this is actually going to become negative. It's going to have more electrons than it should, and that one's going to become positive. Now the connection only exists for a second, because as I crank it, they move on. We go to a new segment, and the original one that we were talking about is now isolated. So that negative charge is stuck there, and the positive charge is stuck here. Now, they're not going to like to be moved away from what's going on the other side. Remember, this all started because the other one on the other side was positive, and that induced negative charge to go into here. So why did it move away? Because I added energy. I did work. And what's happening is that work is being stored by these charges moving away from each other. And the more work I put in, the more energy is stored. The negative charge gets cranked away and it gets brought over to this jar. And these needles collect it and store it over here. The positive charge goes here, and that's stored in this jar. Of course, the exact opposite's happening on the other side. Here, positive charge is coming down and getting stored here, and negative charge is going under and getting stored over here. So this side ends up being negative, this side ends up being positive. And we can take that separation of charge and the energy stored that it represents, and we can use it to do work. There are numerous experiments you can do with the Wimshurst machine, and I would like to show you 3 of them. I'm going to go back and forth between this one, which is at my current school, Manchester High School, and the one at my old school, Southmore High School, because the one there was a little more versatile and was in better condition. But I think between the two, you'll be able to see some of the cool things you can do with this. The main control that any Wimshurst machine has are that you can move the discharge spheres to different distances from each other. We know that how much charge you can hold, opposite charge, on 2 different objects is dependent on the distance, so the closer you get, the more likely you'd expect a spark to be. So you can move these around. Obviously you can spin the Wimshurst machine at different rates. So we'll take a look at that. And then there's these things here, these charge storage devices called Leyden jars, or Leyden jars. And we're looking at the opposite side of what you saw before. So this one, in our previous discussion, we said became negative. This one became positive. Kind of made that up. There's not really a way with the equipment we have to tell that. but let's just stick with that for clarity's sake. You're going to see 3 experiments. At first, with this Wimshurst machine, you're going to see what happens when I crank it at different speeds. You're going to see what happens to sparks between the 2 electrodes at a constant distance when I speed up or slow down. Next, you're going to see on the Wimshurst machine at Southmore, you're going to see what happens when I move the 2 spheres far apart, allow charge to build up in the storage devices, and then bring them together. It's a fairly impressive spark. And then finally, on the other Wimshurst machine, there was actually a control to disconnect the Leyden jars, so all the charge had to be stored in the spheres. And in that case, you can check the geometry of the spheres, how big they are, and you can see what effect that has on static discharge. So we'll do those 3 experiments. So I'm going to start spinning it, and I want you to notice that the frequency of the lightning bolts depends on how fast I'm spinning. If I go pretty slow, they're pretty infrequent. If I start to crank fast, they become nearly constant. We're going to see that as we study lightning rods, that there's a certain amount of charge an object can hold before it breaks down the air around it and that charge jumps. But the important thing here is to recognize that the speed at which I'm putting in energy, the power I'm cranking at, determines how fast these charges build up and how fast the lightning bolts happen. Alright, so now we're going to go back to Southmore's Wimshurst machine. We're going to move the spheres apart from each other. We're going to allow large charge to build up in the 2 Leyden jars, and we're going to bring them together. And large charges are going to build up pretty quickly, and we should see some pretty cool sparks. So let's do it. I learned the hard way never to try to hold both pieces, because I got shocked pretty good one time. Whoa. Like I said, the sparks are fairly impressive when the Leyden jars are hooked up. So all this energy is coming from my muscles. I'm separating charges, just like I could be lifting up a heavy rock, and then if I let go, that energy would be discharged. Alright, so now I'm going to discharge these one last time, and then I'm going to disconnect the Leyden jars so it should be relatively safe. Alright, for this final experiment, I'm going to disconnect the Leyden jars, which I can't do on this Wimshurst, but I could on the other one. And we're going to see about how much charge can build up in the spheres when we have 2 different size spheres. I had one more demonstration I wanted to do with the Wimshurst machine, and that was to talk about why lightning rods are shaped the way they are. Lightning rods come to a point because objects that have a smaller radius actually can hold less charge before they have to discharge it. It has to do with how the electric field builds up on those objects, and I'll show you some examples on the board in the next slide. But I've got the Wimshurst machine, I've got the Leyden jars disconnected, and I'm going to set the small spheres fairly close together, about a centimeter apart. I'm going to turn the lights off so it'll be dark, but you should be able to see that as I crank it, there's a fairly steady stream of charges going. And the reason for this is that the small spheres can only hold a certain amount of charge, and it's a small amount of charge before they discharge. So I hope you guys can see is a fairly steady stream of small, not very bright discharges. So I'm going to try to crank it at the same speed with the small balls removed and replaced with the larger ones, also a centimeter apart. And what we should see if I go about the same speed is we should see discharges that aren't as often but are much brighter. And that's because the larger balls can hold a lot more charge before the electric field gets too big. So again, a centimeter apart. That's about a centimeter. So I'll try to go about the same speed. I know it's very hard to tell, but it's happening less often a little bit, and the bolts of lightning are a little bit brighter.